Hey friends, welcome. Today we are going to discuss molecular spectra, and in molecular spectra we are going to discuss rotational spectra, or it is also known as microwave spectra. Now basically there are two types of spectra, that is atomic spectra that arises due to the electronic transition of the electrons, and there are molecular spectra which arises due to the molecular transition due to the interaction of the molecules with the electromagnetic radiations. And we know that as the frequency increases, the energy of the electromagnetic radiation decreases. And when we see the electromagnetic spectrum, then with the increase in the frequency, we have UV, then we have visible, then we have IR, then we have microwaves, and then we have radio waves. So basically, as the frequency increases, the energy decreases, and under the heading of molecular spectra, we have rotational spectra, vibration spectra, and electronic spectra. So basically, when microwaves, they give rise to the rotational spectra, IR it gives rise to vibrational spectra, and UV and visible they give rise to the electronic spectra. That means that in order to generate a particular spectra, the energy is increasing. That is, for rotational spectra we will obtain with the lowest energy radiation, while for vibration the energy required will be more, and for electronic the energy required will be more. So when we are discussing rotational spectra, it will only be the rotational spectra, but when we are discussing the vibrational spectra, it will be the combination of the vibrational as well as rotation, because the molecule will rotate as well as vibrate. And when we will discuss the UV visible spectra or the electronic spectra, then it will be combination of all the three. So today we are going to discuss the rotational spectra, and basically the rotational spectra, it arises due to the rotational transition of the gaseous molecule by absorbing certain radiations of microwave region, and then the transition will take place. And the necessary condition for rotational spectra is that the molecule should contain a permanent dipole. That means, suppose if we take the example of HCl, so in case of HCl there is an electronegativity difference between hydrogen and chloride. So this will be partially negative charge and this will be partially positive charge, and as a result there is an arising, or there will a dipole moment will arise. Similarly, we can take the example of carbon monoxide. Similarly, we have water molecules. So these molecules, they show permanent dipole, whereas homoatomic molecules, like we have oxygen, we have nitrogen, we have chlorine, then we have hydrogen. So all these molecules, dipole moment does not arise, and as a result they will not show the rotational spectra. Also, molecules like carbon dioxide, which are symmetrical molecules, or which are symmetrical molecules, like we have carbon C double bond O. So there is a dipole moment between this carbon and so this oxygen and this carbon, and this oxygen and this carbon, but the resultant dipole is 0, and hence carbon dioxide will also not show the rotational spectra. So this is also one of the important question that many times in competitive exam it is asked. Several molecules are given and you have to tell that which molecule will show the rotational spectra. So keep in mind that all the molecules which possess dipole moment or permanent dipole moment will only show the rotational spectra. Other molecules will not show rotational spectra. And microwave spectra or the rotational spectra, it arises in the range of 1 to 100 centimeter inwards. So it arises in this particular range. So this also question may be asked many a times. Now moving on to the derivation part. In this, for rotational spectra, we are going to derive the energy for rotational spectra, or energy required to generate rotational spectra of a diatomic molecule, and we will also see the spectra, that is spectral lines, and the relative intensity of the spectral lines. In order to derive the energy, we are considering that we are having a diatomic molecule with masses m1 and m2, and R is the equilibrium bond length. So suppose we have molecule with mass m1 and mass m2, and R is the equilibrium bond length. And suppose if we are considering the example of hydrogen, then this hydrogen and this chlorine, and it is partially negative charge, this is partially positive charge, and as there is the difference in the size of both the molecules, the center of gravity will not lie in the center, but it will shift towards the molecule having higher weight. Okay, and as a result, suppose we are considering that r1 is the distance of the center of gravity from molecule 1 and r2 is the distance from the center of gravity of the molecule having mass m2. Okay, and the rotation axis is perpendicular to the bond axis. Okay, that means suppose this is our bond, then perpendicular will be the rotation axis. Then and then only the rotation spectra will arise. If the rotation axis is passing through the molecule, then it will if it is rotating in this particular manner, then the rotation spectra will not arise. Okay, so the rotation axis should always pass perpendicular to the bond axis, and the molecule should rotate in this particular fashion to generate the rotational spectra. Okay, so over here also the rotation axis is perpendicular and the molecule is rotating in this particular manner to generate the rotational spectra. Okay, the center of gravity Cg, okay, the center of gravity will be equal for this particular molecule and this particular length. So hence center of gravity is defined by the equality of moments about its center, and hence at center of gravity we can write m1 r1 will be equal to m2 r2. Now moment of inertia I for a rigid rotor, we are considering that our molecule is a rigid rotor and there is no change in the bond length is taking place. Okay, so it is behaving as a rigid rotor, and the moment of inertia I from physics we know that it is summation of I mi ri square. So this is the moment of inertia. Okay, where r1 ri is the distance of the particle of mass m1 from center of gravity, and since as we are considering the diatomic molecule over here, the moment of inertia for our case will be I is equal to m1 r1 square plus m2 r2 square, and also total distance is r, and the distance from center of gravity to this particular molecule is r1 and center of gravity to this particular molecule is r2. So I can write r, it is equal to r1 plus r2. Also I can rearrange this molecule in the form r2 is equal to r minus r1. Okay, now over here coming back to this representation, the moment of inertia I, over here we know m1 r1 is equal to m2 r2. So in place of m1 r1 I can substitute m2 r2, and in place of m2 r2 I can substitute m1 r1, and hence we will have m2 r2 r1 plus m1 r1 r2. Okay, so from both this representation we can take r1 r2 common and we will have m2 plus m1. Now further we know that m1 r1 is equal to m2 r2, and in place of in place of r2 we can substitute r minus r1, so m1 r1. And further if we rearrange this particular representation in terms of r1, then I will have m1 r1 is equal to m2 r minus m2 r1. This will go that hand side, and I will have m2 r is equal to m1 r1 plus m2 r1. r1 will be common, and then both these terms will go in division. So I will have r1 is equal to m2 r upon m1 plus m2. Okay, so this will be the representation of r1, and similarly for r2 I will have m1 r upon m1 plus m2. Okay, so both these values of r1 and r2 I will substitute in this particular representation, that is both these values of r1 and r2 I will be substituting in this particular representation. So the value of I, that is moment of inertia, it will become, for r1 we have m1 will remain as such, we will have m2 square r square upon m1 plus m2 square, plus we will have m2 m1 square r square upon m1 plus m2 whole. Now further we can take m1 m2 r square and this particular term common from both these terms, and hence we are left with m1 m2 r square upon m1 plus m2 square into we will be left with m1 plus m2. So both these terms will be cancelled out and we will have m1 m2 upon m1 plus m2 into r square. This will be the value of moment of inertia, and over here this particular term is known as reduced mass, and hence I can write I is equal to mu I square, where mu is equal to m1 m2 upon m1 plus m2. Okay, where this particular term is known as reduced mass. So we have now the value of moment of inertia I, and it is reduced mass into the total bond length or square of the total bond length. Now further, L is the angular momentum, and this angular momentum of any rotating molecule is given by I into omega, where I is the moment of inertia as we have seen just now, and omega is the angular velocity. Okay, that means a molecule is rotating in circles, so omega will be the angular velocity of that particular molecule. And from quantum mechanics we know that the angular momentum L can be written as root of J into J plus 1 H cross, and where the value of J is from 0, 1, 2 and dot dot dot, where J is the rotational quantum number and H is the reduced Planck constant, and with the value of H, that is reduced Planck constant, is Planck constant divided by 2 pi. Now we need to know the energy, and in order to calculate the energy, now for a particle with mass m and moving with velocity v, we know that the kinetic energy or the representation of kinetic energy is half mv square. Okay, that is E is equal to half mv square, where m is the mass and v is the velocity. Now over here in our case the molecule is rotating in a circle, so the energy related, or we can say that the rotational energy ER will be equal to half I omega square, where I is the moment of inertia and omega is the angular velocity. Similarly, this is mass and this is the linear velocity, and over here I is consist of our reduced mass and omega is the angular velocity, which gives the value of rotational energy. Okay, now we will just simplify or just little bit modify this particular representation, and the value of ER I can write it as I omega square upon 2I. Okay, now I omega we know it is equal to L, that is our angular momentum, and hence ER can be substituted by L, or EI can be substituted by L, so it will be L square upon 2I, and further we know the value of L, it is root of J into J plus 1 H cross, and hence it will become J into J plus 1 H cross square upon, I can write 2I. So this will be the value of energy, and further if we just simplify it, we will have ER is equal to J into J plus 1 H square upon 8 pi square I. So this is the value of the rotational energy, and generally the unit of this rotational energy is given in joule, and if we want to convert this energy in electron volt, then the value should be divided by 1.6 into 10 raised to minus 19. So when we divide joule by 1.6 into 10 raised to minus 19, the unit will be in electron volt. And this particular representation we have already seen when we were deriving rotational partition function. We have directly used this particular value, and today we have derived. We want to represent the value of energy in centimeter inverse. Then as we know that energy E is hc mu bar, where mu bar is the wave number, and we can, if we represent the value of mu bar, then that would be the value of energy in terms of centimeter inverse. So we will substitute the value of energy, or we can write mu bar is equal to ER upon HC. So we will substitute this value of energy in this particular representation, and hence we will have J into J plus 1 H upon 8 pi square Ci. Okay, so this will be the value of mu bar, and now the unit is centimeter inverse, because we know that mu bar is the wave number and it is equal to 1 by lambda, and 1 by lambda is nothing but it is centimeter, because the unit of lambda, that is wavelength, is centimeter, and if we do 1 by lambda then it will become centimeter inverse. So mu bar value is centimeter inverse. In many a book this value is written in the form of function of J, and this particular term, that is h 8 pi square C into I, it is made up of constants, because we know that h is Planck's constant, pi is constant, C is velocity of light which is constant, and for a particular molecule or for a given molecule the moment of inertia of that particular molecule is also constant. So this whole term is made up of several constants, and hence we can take B is equal to h upon 8 pi square Ci. Okay, or in a many books it is represented as h cross upon 4 pi Ci. So both are essentially the same thing, and hence we can take B is equal to all this constant, and hence our representation will take the form mu bar is equal to J into J plus 1 B, or I can write B ahead, so it will be B into J plus 1, where B is known as the rotational constant. B is our rotational constant, and mu bar, it is the rotational term, or as I have told in many books it is written as Fj, that is function of J, and this function of J is our rotational term. Now we have our unit in centimeter inverse. Now in order to obtain the value of spectral line, we can either plot a graph of energy versus the rotational quantum number, because only the variable is rotational quantum number. So with the variation in the rotational quantum number, the value of the energy will change. Also we can use this particular representation, that is we can also use this particular representation. So either of the two representations can be used to calculate or to obtain the spectral lines. We will be using this particular representation, and in order to obtain the spectral lines we will be using, or we will be taking the help of a term which is known as selection rule, and this selection rule, it is derived from the time dependent permutation theory, which is a part of quantum chemistry, and we don't need to know it over here. So for rotational transition for a rigid diatomic molecule, the selection rule, it is given by delta J is equal to plus minus 1. Okay, and with the help of selection rule we can identify, or we can say that which particular transition is forbidden, or which particular transition is forbidden and which transition is allowed. So for rotational spectra, or for rotational transition, the value or the change in the value of J plus n minus 1 is allowed and all are forbidden. That means if I am looking at J is equal to 0, then I have to look, or after J is equal to 0 I have to take J is equal to 1, then I have to take J is equal to 2. I cannot take from J is equal to 0, I cannot jump to J is equal to 2. So this transition is a forbidden transition, but J is equal to 0 to 1 it is allowed transition, J is equal to 1 to 2 it is allowed transition. Similarly J is equal to 0 to minus 1 it is allowed transition. So only the change of 1, or only the change of the rotational quantum number by unity is allowed, rest everything is forbidden. Okay, and over here plus sign it refers as the absorption, and minus sign it refers as emission. That means the plus sign means the molecules are transiting to the higher energy states by absorbing the radiations, and minus 1 means they are coming back to the lower energy state by emission of the radiation. And as the rotational spectra is observed as an absorption spectra only, we will be using the selection rule as delta J is equal to plus 1, that is delta J is equal to plus 1 is our allowed transition. If we draw a plot of the value of J with respect to V bar, then at J is equal to 0, V bar will also be 0, because if we substitute J is equal to 0, this will be 0. Then for J is equal to 1, value of V bar will be equal to 1 plus 1 2 and this will be 1, so it will be 2B. For J is equal to 2, it will become 2 plus 1 3 and 3 2s are 6, so V bar will be 6B. And for J is equal to 3, it will be 3 plus 1 4 and 4 3s are 12, so V bar will be equal to 12B, 20B, 30B, 40B and so on. Okay, so in this way the energy will go on increasing, and if we are considering the change in energy, that is what is, or if we want to know what is the spacing between these two lines or what is the spacing between the two transitions, then suppose we are considering that the transition is taking place from J to J plus 1. Okay, the transition is taking place from J to J plus 1, then delta V will be the difference between the value of, or we know that as suppose take a simple example that if you want to change or if you want to calculate the change in entropy, then we write it as S2 minus S1. Okay, so similarly, in order to find the change or in order to find the difference in the spectral line, we will do delta V bar is equal to, or delta V, that is change from J to J plus 1, because only plus 1 change is allowed. Okay, so we will have delta V bar will be equal to V bar of J plus 1 minus V bar of J, and that is equal to, value will be B into J plus 1 into J plus 2 minus B of J into J plus 1, and when we simplify it, we will have B into J square plus 3J plus 2 minus B into J square plus J. Okay, and further if we multiply all the terms by B, then we will have BJ square plus 3BJ plus 2B minus BJ square minus BJ. So this, both these terms will be cancelled out, and over here it will be 2BJ. So we will be having, we can take 2B common, so we will have J plus 1 centimeter inverse. So the delta V bar, that is transition from J to J plus 1, is 2B into J plus 1. Okay, so this is the value of the change, or I can say that this is the difference in the spectral line. That means the transition from 0 to 1, J will be 0, so 0 plus 1, it will be 1 and the value will be 2B. Then transition from 1 to 2, this will be 1 and 1 plus 1 2, 2 2s are 4, so it will be 4B. For 0 to 1 it will be 2B, 1 to 2 it will be 4B. Similarly for 2 to 3 it will be 2 plus 1 3 and 3 2s are 6, so it will become 6B and so on. So in short, for rotational spectrum of a rigid diatomic molecule, we can see that the spectral lines or line series is 2B, 4B, 6B, 8B and so on, and there is an equal spacing between between each line, and the difference is of 2B. So this difference 2B is known as frequency separation. Okay, it is known as frequency separation. So when you look in this particular graph, then from J is equal to 0 to 1, the separation is 2B. Then from 1 to 2, the separation is 2B. From 3 to 2 to 3, the separation is 2B and so on. So there is an equal spacing between all the spectral lines in case of rotational spectra. If we represent this spectra in other way, that is in horizontally, then we will have this, we have J, so 1 2 3 4 5 and so on. So this spacing will be 2B, this spacing will be 2B, this spacing will be 2B, this spacing will be 2B and so on. So hence the spacing between each spectral line is 2B. And if we talk about the relative intensity of the spacing, or if we talk about the relative intensity of the rotational spectral lines, then the relative intensity, it is dependent on the relative population of different energy levels. Okay, and the relative population of different energy levels is given by Maxwell-Boltzmann distribution law, and the intensity of the rotational lines is directly proportional to the Maxwell-Boltzmann distribution law. So I can write intensity, it is proportional to the Maxwell-Boltzmann distribution law, and Maxwell-Boltzmann distribution law is given by Nj upon N0 is equal to Gj, that is the degeneracy. So we will have 2j plus 1 e raised to minus er upon kt. Okay, so this is our Maxwell-Boltzmann distribution law, and it is intensity is directly proportional to the Maxwell-Boltzmann distribution law, and this Maxwell-Boltzmann distribution law, it gives the relative population of any particular system under equilibrium, and it gives the most probable distribution. That means with the help of this particular law, we can say that which is our most probable distribution, and that most probable distribution will be the maximum or will be most dominant. Okay, and if we plot a graph of intensity or Nj upon N0 versus the angular momentum quantum number J, then it is observed that the spectral lines will, or the intensity of the spectral lines will increase, and then it will decrease as the quantum number J increases. That means the spectra we will be having is, we will have a hump or we will have a jump in the spectra, and then it decrease. Okay, so this type of spectra is observed in case of rotational spectra, and the reason is that as the energy levels are increasing, the population of the energy level is increasing, and we know that at a particular state or under equilibrium condition, only a specific state will be most populated, and the value of that particular state will be highest, and that will be the maxima, and again the population is decreasing. Let's explain by taking a simplest example, that is, suppose we are having 100 molecules. So in energy level 1 we have 2 molecules, in energy level 3 we have 5 molecules, in energy level 8 we have 10 molecules, in energy level suppose say 60 molecules, then again in energy level 5 we have say 8 molecules, then 3 molecules, 2 molecules in 1 molecule. So our energy level 4 is most populated, and hence the intensity will be highest according to Maxwell-Boltzmann distribution law. Okay, and this is most populated, so the intensity will be highest, and remaining are very less populated as compared to the most populated it, and hence we will see a mountain, or we will see a graph in terms of mountain in case of rotational spectra. Okay, and the value of J, that is J max, that is at what particular energy state the maximum will be observed, it is given by J max is equal to K T by 2hCb raised to 1 by 2 minus half. So with this particular representation we can calculate J max, and J max should be rounded or should be rounded to the nearest integral value, that is, suppose we are getting 7.85, then J max should be taken as at, because we have whole numbers. Okay, and we are not having integers, so for 7.85 we should take it to, or we should round it off to the nearest 0. Okay, so in this way we can calculate the J max, that is at what particular value of J the maximum is obtained. Over here K is Boltzmann constant, T is the temperature of the system, H is Planck's constant, C is the velocity of light, B is the rotational constant. So with the help of this particular representation we can easily calculate the value of J. Talking about the applications of rotational spectra. First application is, it is used to calculate the bond length. Okay, it is used to calculate the bond length of different molecules. The second is very popular, that is, it is used in microwaves. So basically microwaves are more popular nowadays, and in microwave we can cook food. So basically food is cooked by the internal energy of the system and not by the convectional heat. So in microwave, the water molecule, we know they are microwave active, so they can absorb the microwave radiations, and the excess of microwave radiations absorbed are re-emitted back in the form of heat. Okay, and as a result, because of that particular internal heat, the food is cooked. So this is the principle on which the microwaves are working, and basically it is based on the rotational spectra. So hope the rotational spectra are clear. So today we have discussed rotational spectra for diatomic molecule. We have derived the value of energy in terms of joules, then we have converted that in terms of centimeter inverse. We have seen the rotational spectra or rotational lines. We have calculated the relative distance between each spectral lines, and then we have calculated, or we discussed about the relative intensity of the spectral lines, which is based on the Maxwell-Boltzmann equation. We have seen how to calculate the value of Jmax, and finally we have discussed the applications of microwave. Hope the rotational spectra is clear. Thank you very much.